All right, so get ready because um, today we are diving into the world of databases,
Okay.
specifically a structure called the LSM-Tree.
Sounds fun.
You've sent us some pretty hefty research on this, and let me tell you, it's fascinating stuff. Ever wondered how systems handle millions upon millions of data entries without slowing to a crawl?
It's a problem.
That's where the LSM tree comes in, like a superhero for your database.
What's really cool is that the LSM tree is built for speed when it comes to adding new data.
Yeah,
Something traditional methods like the B tree
right.
really struggle with.
Okay, so paint a picture for me, and for a listener too, of course.
Sure.
What kind of real-world situation would show just how much better the LSM tree is?
So imagine a major bank
Okay.
processing thousands of transactions every single second.
Thousands.
Every single second.
Yeah.
Each transaction updates accounts, sure.
Right.
But it also generates a record in a history table for tracking.
Okay.
Now, this history table grows insanely fast.
Yeah, can I imagine?
Keeping it indexed, especially with the B tree, would mean tons of disk reads and writes, slowing the whole system down.
So it's like trying to add a new book
Yeah,
to a library that's already bursting at the seams.
Yeah.
And you have to reshelve everything to make it fit.
exactly. It becomes a logistical nightmare.
Right.
That's where the LSM tree's unique structure comes in.
Okay.
It's got two main components
Okay.
that work together to streamline things.
Okay.
There's a smaller component called the C0 tree, which
Mhm.
lives in memory.
Okay.
Think of it like a super fast cache.
Right.
All the new data goes there first.
And then there's the bigger, slower storage area, right?
Right. We call that the C1 tree.
Okay.
And it lives on the hard drive.
Okay.
Think of it as the main library shelves.
So it's like having a temporary workspace
Yes.
to sort and organize new entries before filing them away permanently.
Exactly.
But wouldn't that take up a ton of memory?
That's the beauty of it. The C0 tree doesn't need to be massive. It just needs to be big enough to handle bursts of new data.
Yep.
And periodically, in a process we call rolling merges.
Okay.
The data from the C tree gets merged into the C1 tree on the disk in a super efficient way.
Rolling merges. That sounds intriguing. Is it anything like merging lanes in traffic?
It's actually more like merging two stacks of index cards.
Okay.
You have your smaller sorted stack of new cards from the C tree, and you merge them into the larger sorted stack on the C1 tree.
I got it.
But instead of individual cards, we're talking about chunks of data.
Ah, so it's like a super organized filing system that keeps everything in order without constantly shuffling things around on the hard drive.
That's the idea. And to make it even more efficient,
Okay.
the LSM tree borrows a trick from log-structured file systems.
Okay.
It uses something called multi-page disk blocks.
All right.
Basically, it reads and writes large chunks of data to the disk all at once, rather than accessing individual bits here and there.
So fewer trips to the filing cabinet, so to speak.
You got it. And instead of overwriting older data,
Okay.
it just marks it as invalid.
Interesting.
This may seem counterintuitive, but it actually makes recovery from a system crash much smoother.
Oh, okay.
Yeah.
So we've covered how the LSM tree handles new data, but what about finding, deleting, or updating existing information?
Sure.
Does it still manage to avoid those slow disk operations?
Absolutely.
Okay.
When you need to find data, the LSM tree searches both the C0 and C1 trees.
Both of them?
Yeah.
Okay.
Deleting data, it uses delete node entries, which are like little flags marking entries for removal during the next rolling merge.
Gotcha.
And for updates, it simply treats them as a delete followed by an insert.
So it's like having a to-be-deleted pile on your desk, and you only empty it when it's time to tidy up.
Exactly. And this whole approach,
Right.
this deferred placement of data, is one of the biggest reasons the LSM tree can outperform traditional methods.
All right. I'm starting to see why this is such a big deal.
Hmm.
So far, we've been talking about the two-component model. Is there anything else that makes the LSM tree even more efficient?
There is.
Oh.
You see, while a two-component LSM tree is incredibly efficient,
Okay.
we can actually squeeze even more performance out of it.
Okay.
And that leads us to the multi-component LSM tree.
Multi-component.
Yeah.
Okay.
Imagine adding another disk-based component,
Okay.
C2,
C2.
even larger than C1, and maybe even a C3, and so on.
So instead of just two storage areas,
Right.
we have a whole chain of them.
Precisely. It's like having a series of increasingly larger containers for our data.
Gotcha.
And this multi-component structure allows us to fine-tune the balance between memory cost, which can be expensive, and disk cost, which is cheaper but slower.
Interesting. So we're essentially shrinking the amount of pricey memory we need without sacrificing performance.
That's
But
right.
doesn't adding more components make things more complex?
There is a bit more complexity, yes,
Right.
but the benefits can be huge. It actually allows us to make the memory component even smaller, which saves money while still maintaining those awesome batching efficiencies during merges.
Okay.
Plus, there's a mathematical theorem that shows this isn't just a clever idea,
Right.
it's mathematically sound.
Okay, now I'm really intrigued. I always love it when there's solid math backing up a cool concept.
It's good stuff.
So how much more cost-effective is this multi-component design?
Let's look at an example that compares the costs of a traditional B tree to a 2-component and a 3-component LSM tree.
Okay.
The results are pretty impressive.
So the 3-component LSM-Tree would be the most cost-effective solution in this case.
Exactly.
Right.
And the more components you add, the greater the potential cost savings.
Interesting.
Now, it's important to note that while LSM trees excel at handling data inserts,
Okay.
they might need a bit more disk access for find operations compared to B trees.
So if you're frequently searching for specific data, the B tree might still have a slight edge.
Possibly, but we can mitigate that by keeping certain directory nodes of the LSM tree in memory, which speeds up those searches.
Okay.
So it really boils down to the specific needs of your application.
This is all making a lot of sense now.
Good.
So we've covered how the LSM tree is structured, how it handles different operations, and why it's so efficient. But what about when things get really busy? How does it handle multiple processes trying to access or change data at the same time?
Ah, you're talking about concurrency.
Right.
And that's a crucial aspect of any data management system.
Okay.
The LSM tree uses a clever mechanism called node locking.
No locking.
Yes.
Okay.
To prevent conflicts and data corruption.
Right.
It's like putting a temporary do not disturb sign on a piece of data while it's being worked on.
This is like having a traffic cop directing the flow of data to prevent accidents.
Exactly. And it uses different types of locks, like read locks and write locks, depending on what's being done.
Okay.
This makes sure reads and writes can happen at the same time without messing things up.
That's clever. But what about recovering from crashes? How does the LSM tree make sure data isn't lost if the system goes down?
For that, it relies on checkpoints.
Checkpoints.
Yeah.
Okay.
Think of them as snapshots of the system's state at a specific point in time.
Okay.
These snapshots are periodically saved to disk,
Okay.
and they include vital information like the locations of all the data components,
Okay.
the positions of the rolling merge cursors,
Gotcha.
and the contents of the C0 tree.
So if the system crashes, you can basically rewind back to the last checkpoint and rebuild itself from there.
Exactly. And to make extra sure, no data is lost.
Okay.
It also uses a sequential log file that keeps track of all the operations that happened since the last checkpoint.
So it's a combination of checkpoints and logs that allow the LSM tree to recover gracefully from crashes.
Exactly.
But doesn't all this checkpointing slow things down?
Well, it's true that checkpointing does involve some disk writing,
Yeah.
but it's designed to be as efficient as possible. For instance, new data can still be added to the C0 tree while the rest of the checkpoint is being saved.
Okay.
This minimizes any disruptions.
That's reassuring. So not only does the LSM tree perform well, but it's also robust and reliable, even if the system throws a tantrum.
Absolutely. And I think it's important to highlight that the LSM tree's approach to data management is truly a game changer.
Right.
It breaks away from the traditional method of immediately placing new entries in their final order,
Right.
which leads to all those extra disk accesses.
You're talking about how traditional methods like the B tree work, where new data is instantly slotted into its exact spot, right?
Exactly. The LSM tree, on the other hand,
Okay.
embraces deferred placement,
Okay.
which means it holds off on permanently placing new entries until it's most efficient to do so.
So it's like having a staging area where new data can hang out until it's time for the big merge.
Yeah.
No need to rush and cause unnecessary traffic jams on the hard drive.
Perfectly put. And this strategy sets the LSM tree apart from other methods that try to do deferred updates. Okay. None of them guarantee that the initial component for new data stays in memory, which can lead to slower performance.
So the LSM tree's commitment to a memory-resident initial component, combined with its carefully controlled deferred placement, is what makes it so revolutionary.
That's right.
It's not just delaying updates, it's doing it strategically for maximum efficiency.
That's a great way to put it.
I am starting to see how revolutionary this concept is.
Good.
This is so much more than just database indexing. Can you give me an example of how this concept could be applied in a real-world situation?
Of course. The implications of this go far beyond just database indexing.
Okay.
This idea of deferred updates could potentially be used to optimize other data-intensive processes or even real-world scenarios.
Right.
For example, imagine a system for managing workflows like processing orders or approving transactions.
So lots of different actions happening all at once.
Exactly. And you might need to keep track of tons of little changes or logs
Okay.
related to each transaction. These logs might need to be accessed frequently, either by transaction ID or by the ID of the field being updated.
Okay.
This is where the LSM-Tree's ability to store entire records,
Right.
not just indexes, comes in handy.
Okay, I'm following. So instead of just pointing to where records are stored,
Right.
the LSM tree could hold the entire record itself. Why is that a good thing?
By doing so, it can achieve something called clustering by key value.
Okay.
This means that records with similar keys are stored physically close together on the disk.
So it's like arranging your bookshelf so that all the books by the same author are grouped together.
You got it.
Makes finding things much easier.
And in the case of managing workflows, if all the logs related to a particular transaction are stored together,
Right.
accessing them becomes much faster.
Right.
It's a powerful example of how the LSM tree can go beyond simple indexing to actually optimize data organization.
Wow, this is mind-blowing. But I'm curious, are there any other potential applications of the LSM tree beyond what we've discussed so far? Like, is anyone researching new ways to use it?
You bet.
Oh, really?
The research around LSM trees is constantly evolving.
Okay.
And there are many exciting directions being explored.
Like what?
For example, researchers are looking into using LSM trees for time key indexing,
Okay.
which is essential for managing time series data.
Right.
The kind of data you get from sensors, financial markets, or weather patterns.
Right.
They're also investigating how to implement LSM trees in distributed systems
Right.
where data is spread across multiple machines,
Okay.
which is becoming increasingly important in the age of cloud computing.
So the LSM tree isn't just a static solution.
Right.
It's a dynamic concept that's constantly being adapted and improved to meet the demands of new and evolving data challenges.
You hit the nail on the head. It's a testament to the power of clever data structures and algorithms to solve real-world problems and even inspire new ways of thinking about data management.
This has been an incredible deep dive into the world of LSM trees so far. We've covered a lot of ground, but there's still so much more to explore.
Absolutely.
All right, listeners, we're going to take a quick break, but don't go anywhere.
Stay tuned.
When we come back, we'll continue our exploration of the LSM tree and its fascinating applications. We'll be talking about real-world implementations and how this data structure is being used in everything from databases to logging systems. Stay tuned.
Looking forward to it.
All right, see you after the break.
Sounds good.
Welcome back. Before the break, we were discussing how the LSM tree can store entire records,
Right.
not just indexes.
Exactly.
This unlocks a whole new level of organization called clustering by key value.
It does.
You mentioned this could really boost performance in real-world scenarios. Can you walk me and our listener through a concrete example?
Absolutely.
Right.
Let's say you're running a massive e-commerce platform.
Okay, like Amazon?
Sure. Yeah.
So-
Every time a customer places an order, the system generates a bunch of log records.
Okay.
Things like order details, shipping info, payment confirmations, and so on.
So during peak seasons, like around the holidays, we're talking about a truly astronomical amount of data being generated constantly.
You got it.
Wow.
And all of these log records need to be accessed frequently for things like tracking orders,
Right.
processing returns, or analyzing customer behavior.
Okay, now I see where you're going with this. If all those log records for a single order are scattered all over the disk,
Yeah.
finding them would be a nightmare. Kind of like trying to find a specific grain of sand on a beach.
Exactly. But if we use an LSM tree to store these log records and cluster them by order ID,
Okay.
we can dramatically improve access times.
Oh.
All the information related to a specific order would be physically located together on the disk. It's like having all the ingredients for a specific recipe stored in the same cupboard.
So instead of searching the entire warehouse, the system only needs to check one aisle. That's genius. This clustering concept could be applied to all sorts of scenarios, right? Not just e-commerce.
You're catching on quickly.
Thanks.
Anytime you have a large data set where records need to be accessed frequently based on a common key,
Right.
clustering with an LSM tree can be a huge win.
Okay.
It's about making sure the data is organized in a way that makes sense for how it's going to be used.
This is eye-opening. It seems like the LSM tree isn't just about efficient indexing. It's also a powerful tool for structuring data to optimize access patterns. It's like having a personal organizer for your database.
I like that analogy. And this really highlights the versatility of the LSM tree.
Right.
It can be tailored to fit a wide range of applications and performance needs.
Because this deep dive is getting more fascinating by the minute.
Ah,
We've talked about the theory behind LSM trees,
right.
but now I'm curious about the real-world applications. What kinds of systems are actually using LSM trees to boost their performance?
One of the most prominent examples is Apache Cassandra,
Okay.
a popular NoSQL database known for handling massive amounts of data.
I've heard of that one.
Cassandra uses LSM trees extensively for managing its data storage and achieving super fast write performance.
So Cassandra uses the LSM tree's strengths to handle the constant influx of new data that's so common in the NoSQL world. It's like having a super efficient traffic management system for a city that never sleeps.
Precisely. And it's not just Cassandra. Other NoSQL databases like SylDB and RocksDB
Okay.
also rely on LSM trees for their storage engines. It's becoming a standard for high-performance data storage in the NoSQL world.
That's impressive. But are LSM trees only used in databases?
Not at all. They're also being used in other areas where managing large data sets efficiently is crucial.
Okay, like where?
For example, some logging systems use LSM trees to store and index the massive amounts of log data generated by applications and servers.
So instead of just dumping all that log data into a huge disorganized file, they're using the LSM tree to structure and index it, making it much easier to search and analyze, kind of like organizing a library of log files.
Exactly. And this is incredibly valuable for debugging, monitoring, and identifying trends in system behavior.
Right.
It can help pinpoint issues more quickly and prevent potential problems before they become major headaches.
Okay, I'm starting to see the bigger picture. The LSM tree is like a Swiss Army knife for data management. It's a versatile tool that can be used in a wide variety of scenarios to improve performance, efficiency, and reliability. It's almost too good to be true. Are there any downsides or limitations to using LSM trees? Anything we should be aware of?
That's a great question and an important one to ask about any technology.
Yeah.
While LSM trees excel at write-intensive workloads,
Okay.
they might not always be the best choice for read-heavy applications.
Interesting. Why would that be? I thought they were supposed to be super efficient at everything.
Remember that deferred placement strategy we talked about earlier?
Yeah.
New data is first written to the memory-resident C0 tree,
Right.
and then gradually merged into larger components on the disk.
Right.
This is great for writes,
Yeah.
but it can sometimes create a slight overhead for read operations.
I see. So because the data isn't always in its final sorted location,
Right.
the system might need to check multiple places to find what it's looking for.
Exactly. It might need to search the C0 tree in memory
Right.
and then potentially go through the larger components on the disk. It's like having to check multiple folders to find a specific document.
So unlike a B tree, where everything is always neatly filed away in its final position,
Right.
an LSM tree can sometimes require a bit more searching.
That's the trade-off.
Yeah.
For write-heavy workloads, the performance gains from deferred placement outweigh this occasional read overhead.
Right.
But for applications where reads are the dominant operation,
Right.
this overhead become more noticeable.
This is about choosing the right tool for the job.
Exactly.
If you're doing a ton of writes,
Right.
the LSM tree is your champion. But if you're mostly reading data, a B tree or other read-optimized structures might be a better fit.
Got it. There's no one-size-fits-all solution in data management.
Right.
The key is to understand the strengths and weaknesses of each approach and choose what works best for your specific needs.
This is a great reminder that even the most innovative technologies have their trade-offs.
It's true.
It's all about finding the right balance for your particular situation. So even within the world of LSM trees, there are different configurations and optimizations that can be tweaked, right? It's not just a simple on-off switch.
Absolutely. Just like you can customize a car with different engines, transmissions, and tires to get the performance you need.
Right.
You can also fine-tune an LSM tree to match your specific workload. There's a whole spectrum of possibilities.
This has been an amazing journey so far. We've gone from understanding the basic concepts to exploring real-world applications and even some of the potential limitations. But I feel like there's still so much more to learn and discover about LSM trees.
You're absolutely right. The world of data management is constantly evolving, and LSM trees are at the forefront of innovation in this field.
Right.
New research, optimizations, and applications are emerging all the time. It's a very active and exciting area.
This definitely isn't the end of our deep dive into LSM trees. It's just the beginning. Before we wrap up, though, I have one final question.
Okay.
We've been talking about LSM trees in the context of computer science and data management.
Yeah.
But I can't help but wonder if the principles behind LSM trees, things like deferred placement,
Right.
batching efficiency, and strategic organization,
Mm-hmm.
could be applied to other areas of our lives.
Now, that's a fascinating thought.
Right.
I think you might be onto something.
What if we could apply these concepts to managing our time, our tasks, or even our physical belongings? Could we achieve a similar level of efficiency and organization in our daily lives?
It's a thought-provoking question and definitely worth exploring.
Imagine if we could batch our errands, defer less urgent tasks, and organize our homes in a way that minimizes wasted effort and maximizes efficiency. Could we achieve a level of optimization that rivals the performance of an LSM tree?
It's certainly an intriguing idea. It highlights the potential for these concepts to transcend the realm of computer science and influence the way we approach problem solving and organization in general. After all, our brains are essentially complex data management systems, constantly processing information and making decisions.
So as we conclude this part of our deep dive, I want to leave our listeners with a challenge. Think about how the principles behind LSM trees could be applied to your own life.
It's a challenge worth taking on. Who knows, you might just discover some surprising and insightful ways to optimize your own personal operating system.
And on that note, we'll wrap up this part of the episode. But don't go anywhere. When we come back, we'll delve even deeper into the potential of LSM trees and explore how these concepts can be applied to everyday life. Stay tuned. Welcome back to the Deep Dive. Before the break, we threw out a pretty interesting challenge. How can the principles behind the LSM tree, like deferred placement and batching, be applied to our own lives? I'm excited to dig into this.
Yeah, it's definitely a shift in perspective, thinking about these data management concepts in a personal context.
Right.
But I think there's a lot of potential there for optimizing our daily lives.
For example, we talked about creating a CO buffer
Right.
for our to-do lists.
Uh,
Instead of trying to tackle every task the moment it pops up,
yeah.
we could collect them in a temporary holding space.
Exactly. Think of it like an inbox for your tasks.
Yeah.
You can gather everything there without feeling overwhelmed and then prioritize later.
And then periodically we could do a rolling merge
Right.
of our to-do list. We could group similar tasks together and knock them out in batches.
It's about working smarter, not harder.
Right.
Batching errands, emails, or even household chores
Right.
can help us minimize distractions and be more productive.
It's like that saying, if you want to go fast, go alone. If you want to go far, go together. Instead of constantly switching gears,
Yeah.
we can focus on one type of task at a time.
You've got it. And this idea of batching aligns perfectly with the LSM tree's strategy of merging data in chunks.
Right.
It reduces overhead and increases efficiency.
And remember how we talked about data temperature in the context of databases?
Right.
What if we apply that to our personal lives?
That's an intriguing idea. We could categorize our belongings, commitments, and even relationships based on how frequently we need to access or interact with them.
It's like prioritizing the things that matter most.
Hmm.
The items or tasks that are hot,
Right.
meaning we need them frequently,
Yeah.
should be easily accessible.
Right. And the colder items, the things we rarely use or need,
Right.
can be stored away or even let go of.
It's about decluttering and creating a more streamlined environment.
Exactly.
By organizing our lives this way, we can reduce stress, minimize distractions, and free up mental space
Yeah.
for the things that are truly important.
It's all about optimizing our personal operating system, so to speak.
Exactly. And just like optimizing a database, it's an ongoing process. There's always room for improvement and fine-tuning.
Absolutely. It's about being mindful of how we manage our time,
Right.
our energy, and our resources.
So listeners, as we wrap up this deep dive into the LSM tree, I hope you'll take these principles with you and experiment with applying them to your own lives.
It's a challenge worth taking on. Who knows what new levels of efficiency and organization you might unlock.
And on that note, we'll wrap up this episode of The Deep Dive. Thank you for joining us on this fascinating exploration. Until next time, happy learning.